Hi everyone. Today we are very nice to have Hart Goldman from the University of Chicago to talk about composite fermions and composite liquids in the TMD materials.
Thank you, G, for inviting me and having me here. So you already said my message of this talk is going to be the usefulness of composite fermions as an organizing framework for thinking about all of these new amazing experiments in both moire TMDs and now also in pentallayer graphene, realizing not just all of the amazing physics of the fractional quantum Hall effect and zero magnetic field, but also potentially new exotic forms of quantum criticality, new types of charge ordered and correlated phases, and my main sort of message will be that composite fermions are an excellent tool for navigating this new rich landscape. So, remote is not working. There we go. Okay, so this talk is mainly going to be focused on a recent paper from a few months ago with these amazing people, Aidan Reddy and Nitar Paul, who are both students at MIT, and of course Leon. And I also want to mention there was another local paper that came out at the same time describing very similar physics. Those of you who are in the audience who are on this paper, you know, much of what I discuss in this talk is going to be fairly familiar to you. I also want to acknowledge several collaborators on issues that are related to the ones that I will discuss in this talk. So, yeah. Is somebody trying to ask a question? No. Okay. So I'll start with some general philosophical musings, I guess. All of us know that the fractional Hall effect is one of the most rich and beautiful, but also well understood, strongly correlated phenomena in quantum matter. You know, we understand actually a massive amount compared to other correlated systems in nature. In particular, we know ground state wave functions of quantum Hall phases. We know their universe responses, excitation spectrum, and even we know quite a lot about their dynamics. And even with this amazing understanding of quantum Hall, turns out that all of this beautiful physics is actually fairly hard to find in other systems in nature. And one of the main goals of modern quantum condensed matter physics has been to try and find situations which are realistic, in which the physics of fractionalization and topological order can arise beyond the quantum Hall effect. So, in spite of this, I want to emphasize that, okay, we don't understand a lot about quantum Hall, but there are actually many still deep and beautiful open problems just in the original quantum Hall context. So in particular, quantum Hall is one of the poster children for realizing a non-Fermi liquid phase. So if you're filling 1/2, say in gallium arsenide, or filling 1/4, any even denominator filling, I will realize a metallic state. So you see this finite conductivity feature here that I've circled, because that's rho XX there, which we now understand in terms of composite fermions strongly coupled to emergent gauge fields in a manner that is that kills off all of the quasi-particle excitations. And in terms of at least a theoretical understanding, this is probably one of the best understood non-Fermi liquids in nature. yet many of its ground state properties are still mysterious. There are also many things we don't understand about quantum phase transitions, even in the quantum Hall, in the traditional quantum Hall setting. So in particular, if I think about transitions between different quantum Hall plateaus, experiments show that they actually all happen to share the same critical exponents, nu equals 7/3 and z equals 1. And at least for the integer transitions, we can entangle those from fractional transitions. We have at least the product of nu and z being consistent. And that's wild. First of all, we can't explain those exponents to begin with on these systems. And secondly, the fact that you have all of these quantum phase transitions between totally different phases, all sharing the same critical properties, is a complete mystery that still has not been solved. I haven't even gotten to their universal transport properties that we also cannot explain. They all have a universal value of sigma xx and sigma xy that no model has been explained. And also, I think something that is near and dear to many of us is the question of how to generate, manipulate interesting non-Abelian states. Still, actually, there's a remarkable amount that we don't understand in this area. But the main focus of this talk, nevertheless, is going to be new platforms for exploring quantum Hall physics. So I'm not necessarily going to solve these problems, but I'm going to talk about a new context in which, at the very least, we will learn more about them and also introduce new problems. And this is the context of the fractional quantum Hall effect in narrow term band systems. So there was this amazing measurement, which I drew up a plot from here on the right. I guess several months ago in April, demonstrating the existence of incompressible features at fractional fillings of a narrow term band in a twisted TMD system. This TMD system being molyditelluride. So, the special measurement, which was of compressibility, sees a minus 2/3 state, which we interpret via the straight-up formula here. So you see these dark fringes here; those are telling you that the compressibility is going to 0, and the slope of these curves, which gives me d rho by dB here, tells me the Hall conductivity. So you see a 2/3 state here and a 3/5 state. So I'm saying here, even though I'm actually not pointing on the Zoom, but I'm pointing in real life on the far right. So this was an amazing initial observation, and I think at the time we all thought, well, this is great, but of course, in order to confirm all of this physics, we still need something like transport. Now, amazingly, transport measurements did come out. They're shown on the right here from the same group at the University of Washington, and indeed see features with reasonably good quantization of rho xy. This is the red curve at the bottom is rho xx. Doesn't show particularly amazing features here, but rho xy, you see all kinds of interesting, at least somewhat quantized features at 3/2 and 5/3, or sorry, 3/2, 2/3 and 3/5. This is rho xy, and the filling is inverse of that. And interestingly, also observed is this feature where the Hall conductivity or Hall resistivity is close to 2. Oh, all this, by the way, is in units of h over e squared. And the system seems rather metallic, which is reminiscent of this composite Fermi liquid that I was mentioning a couple of slides ago. And something that really is additionally amazing about this system is you get an additional tuning knob in the form of displacement field. There's an electric field perpendicular to the sample that essentially tunes the width of the flat churn band that's realizing this physics. And you see transitions from quantum Hall states to from these quantum Hall type states to more resistive states, which I'll discuss in a bit more detail later. Okay, and so even more surprising is just recently the same type of physics was observed in very quite different material, rhombohedral pentalayer graphene on HBN. So this is a graphene system, rather different microscopics, and nevertheless, they managed to find, this is from a group at MIT, Long Ju, not just the 2/3 and 3/5 states, but also additional features which look like fractional quantum Hall states in the Hall resistivity at here it's 3/7 and 4/7. So really remarkable that in this system you see even more fractions, and also very similar overall structure to this resistivity plot to the TMT, which I at least think is very surprising and is signaling that a lot of this physics is universal. Yeah. So, why be interested in this physics if it's just quantum Hall but it's zero field? Well, I argue that all of the big questions in quantum Hall require much more character in the zero field setting, and the reason for that is in ordinary quantum Hall systems, phase transitions are tuned either by filling, or you imagine tuning them by disorder. So I can access, go back here, the sort of global phase diagram of the quantum Hall effect with these two axes. Rho XX here, classically describing the disorder, and rho XY you can think of as like the field direction here. And we can then model the landscape of quantum Hall states using this overall picture, with these crosshatched regions here being these composite Fermi liquid states. But in the zero field setting, now we have this displacement field that I mentioned, and we have all kinds of additional competing phases, such as Fermi liquid metals and charge density waves, maybe even superconductivity that are also possible, which, as I already said, probably 2 or 3 times, could lead to new exotic kinds of phase transitions. And so what I'm going to argue here the rest of this talk is that an organizing feature of the phase diagram of these systems is going to be a composite Fermi liquid metal, again, in U = 1/2, which I already at least signaled to you guys in the earlier data. Okay. So before I get to that, I need to acknowledge a certain question of terminology. So I've been saying fractional quantum Hall so far. I'm going to switch to using the phrase fractional quantum anomalous Hall to describe zero field states. I happen to like that terminology as describing generally fractional quantum Hall topological order, which is stable in zero magnetic field. Now, there's an additional term which many people use as well in this setting, which is that of fractional churn insulator. So, from my point of view, FCI is also a great piece of terminology that describes any fractional quantum Hall topological order, either at zero or a finite field, which is enriched with the symmetry of an underlying lattice. Okay, so we kind of need this as an umbrella term, at least from my point of view, and FQAH describes something more specific, and so I'll maybe make the perhaps controversial statement that to me all FQAH phases are FCIs, but it's not at least immediately obvious that all FCIs have a stable realization at zero field, and in that sense are FQAH. Okay, so just some roadmap for the rest of the talk. First, I will discuss the physics of the composite Fermi liquid in the Landau level setting and the use of composite fermions in organizing the fractional quantum Hall phase diagram. Then I will actually talk about the specific case of moire telluride, proceed to discuss the zero field composite Fermi liquid that can be realized in this setting, how it organizes also the phase diagram of that system, and make some final additional comments, time permitting. Okay, so some introductory spiel about the fractional Hall effect. We all know that we just take a 2D electron gas in the perpendicular magnetic field. The electrons are going to form extremely highly degenerate Landau levels, and realize when the Landau levels are filled, phases with integer Hall response. This is the integer quantum Hall effect. And then in the presence of Coulomb interactions, you can then get fractional features, here shown 2/3, 2/5, and so on. And again, in addition to all of that, you can see even denominator fillings here, perhaps more clearly than the previous slide, these composite Fermi liquid states. Okay, so composite fermions provide an organizing framework for all of this. I can start with my system of electrons in a magnetic field and always adiabatically attach fluxes to them to map my original system to a system of what we'll call composite particles coupled to an emergent Chern-Simons gauge field and feeling a screened magnetic field, where the screening is proportional to the density of the number of particles I'm attaching flux to. And depending on whether this M here in this expression is even or odd, I'll either attach even number of flux quanta, in which case Berry phase shifts by 2 pi, my statistics remain the same, or not Berry phase, sorry, Bohm phase shifts by 2 pi. Or if I attach an odd number of flux quanta, I'll get my statistics shifting by pi, and thus get composite bosons. So if I'm going to focus primarily on the composite fermion case, it turns out that most observed fractional quantum Hall fractions can be explained as integer quantum Hall phases of composite fermions. So I start with, say, attaching 2 flux quanta, I fill a Landau level of these composite fermions by doping, and I get, well, say I fill P Landau levels actually, and then if I compute the resulting filling fraction of the electrons, I get the classic Jain sequence. Fractional states, which actually describe most of the states that we have in nature. Okay. Now, if I look close to half filling, so this is like taking the limit as the effective magnetic field felt by the composite fermions goes to 0, I will get now a Fermi surface of composite fermions. Okay, because these are fermionic objects, they don't feel a magnetic field, they're going to want to be of metal, but they remain strongly coupled to this emergent gauge field. This is the famous HLR Halpern theory of the half-filled Landau level. Simplest, in my view, the simplest non-Fermi liquid. And yeah, as I said before, I just form integer quantum Hall states of these things, I get Jain sequence states, and also I can actually explain some non-abelian states using these guys through pairing. Now, this composite Fermi liquid theory has seen a huge amount of phenomenological success. It predicts a great deal more than just the Jain states. It also explains quantum oscillation measurements. So, one example is I can introduce a periodic potential with some wave vector Q, and I'll expect magnetoresistance minima as I tune away from nu equals 1/2. So now the composite fermions are feeling a magnetic field. They're going to form cyclotron orbits. And I'm going to see magnetic resistance minima when those cyclotron orbits are commensurate with periodic potential. And actually, this composite Fermi liquid theory beautifully predicts those kind of experiments. Well, modulo recent, somewhat recent experiment that still people are working on explaining, but vast majority of quantum oscillation experiments can be explained extremely well using this framework. But there are still many open questions associated with this theory, in particular the realization of particle-hole symmetry, which is a problem that's been near and dear to many of us for a while, and also questions related to the dynamics of the composite Fermi liquid. In what sense is it truly a non-Fermi liquid? Can you get non-Fermi liquid transport in something like this? It was ultimately the ground state physics of the composite Fermi liquid. All of this is still rather poorly understood. All right. So now I want to take this physics and pour it over to zero field. So how does one actually do this? Well, you need a few ingredients. First, I need to get rid of time reversal symmetry without an external field. So I need to do that spontaneously. And this can be done, for example, by ferromagnetism. So I need to at least start with something that can give me a ferromagnet. By the way, as a comment, anyone online can just interrupt me with questions at any time. Yeah, the mic is on, so yeah, I don't mind interruptions. Now, with this time reversal breaking, one then would also need to form narrow Chern bands. So these are fairly flat bands which look like Landau levels. Okay, so by flat here, I just mean that the dispersion of the band is much smaller than the Coulomb energy. And as a result, then, if you're sufficiently like a Landau level, the projected Hamiltonian, which I've written here, into the band will at least well resemble, and there are ways of precisely characterizing this. I won't get into that in detail in this talk. The physics of projection in the lowest Landau level. So in the lowest Landau level case, you have no dispersion, they're perfectly flat, and you have ordinary Coulomb density interactions, and the projected density operators satisfy what's known as the GP algebra. Here will be somewhat more general than that, but we want a sufficient resemblance still in level physics. Okay, and it turns out that at least TMD systems like the moly ditelluride system that I mentioned, I showed data from earlier in this talk, are actually quite good candidates for both of these properties. So because of strong spin orbit coupling, you get locking of the spin and valley degrees of freedom, which provides the possibility of having Ising ferromagnetism. So I could spontaneously have all my electrons stay in one valley versus another valley, and that would give me a good ferromagnet. And via twisting and displacement field, you can design a relativity flat band. Sorry, there's a question? Okay. All right. So I'll explain briefly how we microscopically model this problem. So we can focus on the microscopics of a twisted moly ditelluride homobilayer with twist angle set close to 2 degrees, and can write down a continuum Hamiltonian for this that has been developed by other folks. Here, these V's correspond to the moire potential, and the T's on the off diagonal are the interlayer tunneling. And we fit these parameters to results from DFT. So one should mention there was this other paper that I mentioned at the beginning of the talk that sees similar physics to us. They use different DFT parameters from the ones that we chose to use. That's, I think, awesome that with both sets of DFT parameters, you see similar physics. But in any case, the single particle spectrum that you can compute out of this thing contains a narrow c equals -1 band shown down here. I realize I keep saying down here, but the folks at home can't see my face. Well, hopefully context one. All right. Good. So now I can take this result and I can form a projected Hamiltonian into this band with Coulomb interactions. And this is the thing I'm going to be studying, or not me, Aiden, who actually does the numerics, in exact diagonalization. So I have this first term here, which is the dispersion of the band, and the second term here is the interaction term. And I'm going to include spin and valley here to form these sigmas, and use the dispersion and Coulomb matrix elements I get from microscopic. All right. And as I already said, we're going to study this Hamiltonian in ED, but I first want to motivate what its ground state properties are going to be by developing a similar theory of composite fermions that I discussed before in the context of flux attachment at the Landau level, for the case of what I'm going to call for the rest of this talk an anomalous composite Fermi liquid. So we see a composite Fermi liquid zero field at half filling, and then taking that composite Fermi liquid, I'm going to dope it and form fractional non-Hall states eventually. All right, so we can try and construct the composite fermion framework in Chern bands in 3 ways. The first might be, okay, we try ordinary flux attachment, but this is actually somewhat awkward to do in the context of a Chern band. You don't have an external magnetic field. Heuristically, you can get the right answer with this, but in terms of constructing a systematic equivalent to flux attachment, it's certainly at least not straightforward. There are analogs of lattice flux attachment that have been developed, and those involve using lattice consignment theories, and it's a bit of a it's rather involved especially for modeling real systems. Option 2 is to try to project into the Chern band and directly work out the composite fermion picture in the non-commutative space of the Chern band itself. This is a very hard open problem. I can solve it in particular settings, which are related to Landau levels, but certainly not this more general setting. But anybody who's interested in this direction should feel free to talk to me or send me an email. It's a very interesting open problem. And option 3 is, when in Cambridge, do as people in Cambridge do, partons. Okay, so the parton framework has a advantage of, while you can generate tons and tons of states with this, you can do it in fairly general band structures, okay, as a way of generating valid effective field. So I'm going to start with my moire superlattice filling as n equals 1/2. I'm going to split the electrons, which I'm denoting by C here, into a bosonic parton phi and a well, I'll call it composite fermion psi. And I'm going to have this holon here, or the bosonic parton, carry the electric charge, which I'm denoting by this background gauge field capital A. Okay. And I'm going to treat the moire potential as a periodic scalar potential as well. So in a sense, I'm hiding it in big A. And as a result of this, phi is going to see the same band structure as the underlying electrons, and it's going to half fill a C equals -1 band. Well, that gives me a incompressible state, it's a bosonic Laughlin state, at a zero field, and I can integrate it out. Now, part of this involves making some statement about how the spatial symmetries are realized in that state. I'm going to assume that they're realized a trivial way, but that's not an absolute necessity, and it's exploring the different kinds of possibilities for generating states with interesting symmetry fractionalization from composite fermions is, I think, an interesting open direction that I and others are working on. So, okay, what do you get when you integrate out this phi? You get a TQ of T, which looks just like a bosonic Laughlin state. You have this level 2 Chern-Simons theory, mutual Chern-Simons second term, and then you have this additional third term, which essentially fixes the filling for you without needing an external magnet. And you can think of that as like a charge density that's glued to the underlying periodic lattice. Okay, so I can integrate out this auxiliary field B here that I got from integrating out the boson, and you get a resulting theory which looks very similar to HLR. So the main differences with HLR are that I have this curly V here, which models the moire potential. So it will have it's a renormalized potential, which will have the same period as the moire potential. And I will also have this term involving this rho bar here, which again fixes the filling. Okay. And yeah, in particular, you can see explicitly how this fixes the filling by looking at the equation of motion for the time component of little a. Which is by the way, all these A's are U1 gauge fields. Big A is a probed background. Little a is dynamical. And yeah, A sub T's equation of motion gives you a constraint fixing psi dagger psi, which is also my electron density, to the sum of the emergent magnetic field associated with little a and rho bar here. So when the composite fermions feel no magnetic field, so the B star is 0, then the physical density is just, and the physical filling is just the electronic. And if I fix to half filling, then indeed the composite fermions feel no magnetic field, form what we dub an anomalous composite Fermi liquid metal, and we get remarkably similar physics to the ordinary composite Fermi liquid. Now, I want to mention, if you'd like, I'm carrying this rho bar around, but it's perhaps less mysterious if I rewrite it as the curl of some background vector potential, which you can think of as being associated with the magnetic moments of this ferromagnetic state that I'm starting from that breaks time orders. It's kind of a, that's a sort of heuristic analogy, which is why I emphasize using this notation of just using rho bar rather than a mutual Chern-Simons term with curly A. Yeah.
So in the Parthenon framework, is the M star equal to the bare mass or the tandem mass?
I guess in the
I would think that the gauge field is
the gauge field will renormalize this. So it's a question of I guess in terms of
the Parthenon decomposition, technically you only have the A0.
That's right.
And the AI gets generated.
Yeah.
So it's, I guess it's a little different from the ordinary HLR. Like say you do HLR for the ordinary fractional quantum Hall effect, filling. If you just do naive flux attachment versus Parthenon, you'll get different values.
That's right. Yeah.
Just wanted to clarify.
Yeah. Okay. Now, how do we actually justify this beyond heuristics and effective field theory? So we can do ED on a microscopic model I mentioned before, and first get results that are actually amazingly similar to the Hatfield-Landau. So we start by first looking at the half-Landau level case. You get this ground state degeneracy here. So you just want to look at the bottom of these plots mainly. Then if I look at the Chern band case that's modeled after moly ditelluride, you get something that's very similar. Okay, and match up extremely well. And you can think of these states as tiling a Fermi surface, the most compact Fermi surface I can write down in the Moire-Grillemont zone. So I fill center state, and I start filling these states around here, and one additional to that that I can place anywhere. Now, importantly, so these plots over here, notice they're all green. The reason for that is that these things are looking for the overlaps with block states. So what this is telling you is that you have this metallic state, which does not have any overlap with like some overlap, but there's very small overlap with a metal formed of block electrons. In contrast, if I change my twist angle from 2 degrees to 4.5 degrees, my bandwidth gets less narrow. And I actually get a state that looks more like an ordinary Fermi liquid metal in the sense that I just fill up. So the band minima are actually around the edges here. Red denotes large occupation. And I just fill up the edges of the Brillouin zone. I'll get to this top right corner here of 3/4 in a second. So there's some comments on some of the specifics of the ED. We did finite size ED, Aiden did finite size ED on a torus with 16 flux quanta using the projected model from before. I'll erase this. Already said this. Now, yeah, I also want to emphasize that, again, local people also did similar type of ED analysis using different DFT parameters and got very similar results. They also did amazing DMRG. We didn't do DMRG. Okay, so now, I guess I'll comment first on the 1/4 state. So you can also play the same game with the 1/4 state, or not 1/4, 3/4 state, and see similar composite Fermi liquid type features. So you can match this with the Landau level at 3/4, and actually I think that the matching of the spectrum looks even better than the matching of the spectrum for 1/2. I thought I had a slide showing that, but maybe it's actually after the next slide. Okay, so now since this original work, Aiden and Liang have been able to slaughter this problem at even larger system sizes and find amazingly that the composite Fermi liquid is extremely robust. You can go to twist angles where other fractional anomalous Hall states all die, but the composite Fermi liquid stays alive. That's crazy. So yeah, it really emphasizes the centrality of the composite Fermi liquid to the FQAH phase type. All right, now, okay, yeah, there's a slide on 3/4. Yeah, so you can see the matching here for the 3/4 case between the lowest Landau level spectrum and the actual spectrum for the Moire case. And you see actually these, even the excited states match on each other pretty well. All right. Now, I can play the usual game of generating Jain sequence states using this composite Fermi liquid by filling Landau levels. And I get the usual prediction of here now, quantum anomalous Hall states at 0 field at these filling fractions, the usual Jain ones. N equals P over 2P minus 1. Okay, so just the mechanics of how I do that can say dope the ACFL by changing the electron density, now the composite fermions will feel a magnetic field and fill Landau levels. And this results in a resulting electron density when I fill P Landau levels of composite fermions equal to P over 2P minus 1. And as in the ordinary case, you can think of the composite Fermi liquid equivalently as the P goes to infinity limit Jain sequence states. All right, so we can also do ED looking for the Jain sequence phases and indeed see that they're very robust. That's further evidence for the composite Fermi liquid. You see robust states on the Jain fractions. That's giving you a hint that the parent of all these guys is the composite Fermi liquid. And so here's some evidence for 2/5 and 3/5. You see the right topological ground state degeneracy of 5 here. But amazingly now, Aiden can go to even more states and more twist angles and see all kinds of fractions. So here are the gaps depicted for various, for 2 different twist angles. One is 2 degrees, the other is closer to 3 degrees. And you see that for the 2 degree case, you actually get gaps opening up in ground states that correspond to several Jain sequence filling fractions, whereas at larger twist angles, these states will become unstable to things like charge density wave order or metallic features. Okay, so what are the actual experimental observables associated with composite Fermi liquid beyond just Jain states? So the first thing is that in sufficiently clean systems, this is really the most stark thing one can look for, is a large DC Halling. Okay, and that's actually already seen in recent experiments. So you see this Hall conductivity near half filling, or Hall resistivity near half filling, which is close to 2h over e squared, whereas the longitudinal resistivity here is quite small. This is in the MOT2 case. In the pentalayer graphene case, it's a little bit worse, but it's still, the Hall angle is still quite large. Okay. Now, that's not a smoking gun for the existence of a composite Fermi liquid state. When you have a metal, you should see quantum oscillations. Something that is unique about this anomalous composite Fermi liquid state as opposed to an ordinary composite Fermi liquid in, say, gallium arsenide, is I have this periodic potential built in. So I don't need to add anything else in principle to see quantum oscillations. I can just tune the density, which causes the composite fermions to feel a magnetic field, and look for commensurability oscillations with the underlying layer of superlattice itself. So, yeah, as I already said, I tune away from 1/2 with no external fields at all. I should be able in principle to see quantum oscillations, and in particular find resistance minima, where which is set by the Fermi wave vector and the moire superlattice wave vector. Okay. Good. So I already alluded to some of this, but just want to emphasize what experiments have actually seen. So first, an extended region of metallic behavior has been seen close to half filling with Hall resistivity close to 2 and RXX reasonably less than RXY. See the Jain sequence, or the beginnings of the Jain sequence at the very least. And something that's not yet seen, though, is these commensurability oscillations or more direct signatures. And that may require much cleaner systems. Now, I also want to emphasize some additional features in these resistivity plots that are not immediately explainable by the ACFL. In particular, one example is if you look at the transition from, say, the 2/3 state to the 3/5 state, you notice that the Hall resistivity drops between these two states. That's rather unlike anything that we see in gallium arsenide. We normally would have expected something more like a plateau, or at least an increasing Hall resistivity rather than decreasing. Okay, understanding this in terms of doping a composite Fermi liquid is still an open problem. I think it's a very interesting one. All right, so now I'll comment a little bit more on quantum phase transitions. So, as I mentioned at the beginning of the talk, we now have this additional axis of displacement field. And that can in principle tune us between all kinds of different things. Composite Fermi liquid and Fermi liquid, which has already been observed experimentally, can get fractional quantum Hall in insulator, fractional quantum Hall in metal. You can sort of pick your favorite combination of things. And even if they're not seen, you can in principle think about these types of transitions. Now, however, only some of these types of quantum phase transitions are explainable using standard Bartonic techniques, in particular the composite Fermi liquid to Fermi liquid transition and the quantum anomalous Hall to CW transition. But some of these features are actually quite unexplained. So even in the experiments, there are signatures which, sorry, at home it's hard to point at these things, but if you look, say, near filling one here, there's a churn insulator. And as I tune displacement field, you see that there's a little bit of an increase in the resistivity that would indicate the onset of metallic behavior. And you can see similar things for the fractional states. That indicates the possibility of something like a quantum anomalous Hall to metal transition, for which there's no theoretical foundation. That's an extremely interesting and important open question. All right, so before I conclude, I just want to say that I found all of this extremely amazing. I think that's it's rare to see experiments like this that show us things that we know and also things that we don't know. And I think this whole field invites us to think about an interplay of correlations and topological order and different types of quantum criticality that hasn't been seen in an experimental setting in quite some time. So, with all of this, unlike usual mysteries in strongly correlated quantum matter, we have actually clear conceptual tools coming from quantum Hall physics, in particular composite fermions. Okay, and through many future directions here, still growing. I think the field is rapidly growing. More experiments will lead to even further things. But in my last few minutes, comment on one particular additional avenue, which is dreaming up multi-layer systems that are not realized at finite field and exhibiting novel types of quantum criticality. So this is work with different people that will appear hopefully in the next couple of months. Darius is in the room. These other two apparently declined to show up, but thank you, Darius. You start with bilayer now of a composite Fermi liquid at zero field, and it's time reverse conjugate. So imagine you have one magnet pointing the up direction, the other pointing the down direction, and you put them together, and both are realizing this ACFL state. So this is, of course, not possible if you were trying to use quantum Hall multi-layers. You would have an external magnetic field. You wouldn't be able to do something like this. Now, I can try and couple this to an order parameter which pairs composite fermions with what we'll call composite holes between these two layers, and actually generate a non-Fermi liquid or composite fermion metal to mod insulator transition, or what I'm calling a mod insulator transition, with a neutral Fermi surface. So that occurs when this phi here, this order parameter field condenses. Okay. So why might I be interested in something like this? You know, I guess I could imagine trying to set something like this up. We're working out the details of what might be a realistic experimental protocol, but yeah, I can at least think about this in theory space. It's a CMSA talk after all. So I can imagine, say, trying to change the distance between these two layers to tune this kind of transition. And the cool thing about this is that at the critical point, you actually get non-Fermi liquid counterflow. So if I compute the optical resistivity, I will see non-Fermi liquid scale. This is actually really hard to find in transport in HLR, in just single composite fermion. But in the context of this particular example, this ends up popping out rather naturally, at least with some calculation. This can be shown in controlled calculation. So that's going to be upcoming work. I should emphasize, this kind of scaling in transport, which is totally universal, is not possible in the simplest models of non-Fermi liquids at quantum critical points that we study. This was shown in some earlier work also with Darius and Dominic Else and set forward. All right, with that, I'll conclude and take questions.
Whether the composite fermion between the layers will be attracting function or repulsive?
Sorry?
The composite.
Oh, the bilayer?
Right.
It's repulsive. That's why you can get this difference. Because in the ordinary cases, there's an exciton instability that generically happens. That system would be. That's why, like, if I were to take like 1/2 on 1/2, this would not work. Because the composite fermion is just always one pair. The point is that here I can get a fixed point that actually has a finite exit. Yeah, that's the. I didn't emphasize that for time, but that's the trick that's being used. Yeah.
So can you contrast this like fractional parallel of omega with the analogous fractional parallel that some people say for electronic systems? I think there's some subtleties with the latter due to conservation.
Right. So first of all, this is more singular. I think you're talking about the T to the 4/3.
Yeah, I don't remember.
Yeah.
Numbers.
Yeah, so you can estimate the transport scattering rate in like Hertz millisecond periods. That's like T to the 4/3, and there's an expectation that appears in transport, although actually diagrammatic cancellations it doesn't. Over the years, people have argued about whether it can really be there because there's no momentum relaxation, but that's not really an issue here. I think
Because here, I guess current can flow with no momentum.
exactly.
Yeah, the current and momentum.
Yeah, it's not a Galilean invariant system, so you wouldn't. You don't need for there to be additional sources of momentum relaxation. It's to get temperature dependent scaling.
Yeah, but I guess even if you break Galilean invariance, if a finite momentum state carries current, then momentum relaxation. You get momentum relaxation. But here you're saying a non-zero momentum state carries no current. It's like a balance between poles and electrons.
Yeah.
And if we consider transport one of them, we still have an electron. Then there's a correction key, which still has this thing.
I see. So the delta functions cancel out.
Exactly.
I think we have one question from the room audience.
Okay.
Can I mute?
Yeah.
Hi, thanks for the nice talk, Hart. So I wanted to take you back to I wanted to take you back to something that you said was already not innocuous. So this projection into the Chern band to get a projected Coulomb. Have you thought about how that process. I appreciate that this is the simplest thing to do, and it gives good results. Have you thought about how it might be controlled, or is there some
You're
sense
worried
in which
about
the
things
other
like that.
terms?
You're worried about effects from mixing on these results.
Not just mixing, but other terms that might, for instance, not be local, like transport, like correlated transport induced by a projected Coulomb, things like that. Even if we don't worry about mixing, are there other terms that besides projected Coulomb that could be relevant, could be important?
So the projected Coulomb is will always be the dominant interaction energy scale. So like I guess in principle you could have higher body interactions or something, but those will always be weaker than those will always have weaker effects than the Coulomb. But I mean, yeah, in principle one could try to add such things. I don't really know physically what they would correspond to, but I guess in principle you can always add anything that's consistent with symmetry there.
Yeah, I guess I'm thinking about correlated hoppings, like density times C dagger C, or pair hoppings, like.
Oh, I see. Yeah, I have not thought about the effects of those. My collaborators may have. We certainly thought.
Could I comment on that actually?
Oh, Nisharga, you're here. Okay, good.
No, yeah. So this is Aiden, also joining in from Nisharga's laptop.
Yeah.
So,
Hi.
hi. Yeah. So, the band projected exact diagonalization calculation is done in momentum space. So it takes into account like the exact single particle dispersion of the block states in this churn band, and it takes into account all the all the microscopic Coulomb matrix elements. It's not just putting it on a lattice and only taking nearest neighbor repulsion, for instance. So you're talking about like correlated hopping terms. In principle, those are all contained in the projected interaction model.
I see. So it's just have you tried turning off everything except projected density, and does it change any of your exact diagonalization results?
No, I haven't tried doing anything like that.
Because I think the picture that I got from the talk was that the important thing was the projected density, and this is a simple story and sounds reasonable. But what you're saying is that anything else that beyond that was also included in the ED, and I just didn't catch that.
Yeah, so I mean, I guess the interaction that we're projecting is a standard Coulomb interaction, and once you project the Coulomb interaction into a band, and the wave functions of that band aren't just delta functions at lattice sites, then you always end up with kind of these interaction terms that don't really look like density interactions if you were to write them in a lattice model, but they always originate from just a standard density Coulomb interaction when you have wave functions that are not perfectly localized.
Got it. Thanks.
Thanks, Aiden.
Yeah.
And any other questions?
I have another question about the phase stack. So what the numerics showed was that
Aren't you my collaborator? Why are you asking me questions?
No, phase diagram for numerics.
Okay.
Not nothing I did. So there was one phase diagram where at 2/3 you see a fractional quantum pulse data, at 1/3 you see a CW insulator.
Right.
Is there a qualitative understanding of what's going on?
There's strong particle symmetry ranking. Actually, Aiden wrote a separate paper on that, but you can see it fairly naturally, just analytically. by.
So in the experiments, they also try to, so they saw 2/3. They try to look for 1/3.
Yeah, I mean, presumably if you go by its numerics, you go to more optimal twist angles. But
Is there some approximate particle hole symmetry at this optimal twist angle?
I believe particle hole symmetry is still broken. Aiden, is there a sense in which you think that there's an emergent particle hole symmetry or something at 2 degrees or?
Yeah, so two things that I'd like to say. First is there is some experimental evidence for a charge density wave at filling factor 1/3 in devices where there is a fractional quantum anomalous Hall state at 2/3. So in particular, you can take a look at there's a Nature paper from the group of Kin-Fai Mak and Ji Shan, and yeah, so there is some evidence for that charge density wave state experimentally. And regarding the question of some sort of particle hole symmetry, what we find is that near some magic angle, if you'd like to call it that, which given the DFT parameters that we're using seems to be somewhere around 2 degrees, but there's kind of a big error bar and uncertainty on that, I'd say, due to just uncertainty of the DFT parameters. But if you take our model and you go around this magic angle, what you find is that, and you do band projected ED, what you find is that at every filling fraction, the system seems to be almost identical to band projected ED of the lowest Landau level. And because the lowest Landau level, and any Landau level for that matter, has particle hole symmetry, when you're close to this magic angle, the TMD continuum model also seems to have approximate particle hole symmetry.
Because I guess that's the question, is whether there's ever a sense in which it's exact. I don't think there is.
Yeah, I don't think it's ever exact, but basically what I'd say is when you get close to this magic angle, the band projected model becomes almost identical to the band projected model of the lowest Landau level, and therefore it very approximately has particle asymmetry. But I don't think that it will never be perfect as a function of just tuning the twist angle.
Also, as an additional comment, even if you're in a regime where you're realizing like the full, like both branches of the Jain sequence, if you have broken particle hole symmetry, there's no, like, you can still have that, but there's no guarantee like the gaps will be the same. So yeah, I think in Aiden's data, those gaps look pretty similar, but like, there's no reason why that may just be an accident.
Just the band projected interaction can break the particle hole symmetry.
That's right.
You're writing a very careful way.
Okay, so if there's no further question, let's stand by again.
Yeah, thanks everyone.